Hey everyone, welcome back to another video by Camroom 5. In today's video we're going to start to talk about electrochemistry and we'll try our best to understand how electrode potentials work. For that we need to imagine a beaker containing copper 2 sulfate solution and there's a piece of pure copper metal dipped into it as an electrode. In the aqueous solution you have copper 2 ions and in the pure copper you have the metallic lattice of copper with all the delocalized electrons and stuff. Now there are two entities both containing copper, the metallic lattice with the atoms and the copper 2 ions. Now the copper 2 ions can easily gain electrons from the metallic lattice from the delocalized C and they can become copper atoms. So there's an equilibrium established where copper ions can become copper atoms and copper atoms after losing electrons can become ions. So the idea is that there's an equilibrium between the copper of oxidation number 0 and the copper ions of the oxidation number +2. But the question is this equilibrium going to be existing between equal amounts of the ions and metals? So not true, that's not happening. Because when the equilibrium is established, it tends towards the right. Why does it tend towards the right? Why does it try to produce more copper and less copper ions? The reason is that copper ions gain electrons readily, while copper atoms do not lose electrons. Copper is pretty stable as a metal, so copper 2 ions readily gain electrons. And when we talk about copper atoms do not lose electrons. As a result, you will have a higher amount of copper and lesser amount of ions. But in order to compare the electrode potential, we come across a definition known as standard reduction electrode potential, or you can say standard electrode potential. For that you can see there are two beakers, not one. Both these beakers are going to be representing half cells. These half cells have specific electrolyte in them and electrode. For example, the half cell on the left hand side is a copper 2 and copper half cell. But what kind of half cell is on the right hand side? Well, basically you can see an inverted test tube with a black colored block in it. On the left hand side we can clearly see that there's a copper electrode and copper wire connected with the voltmeter. The solution, we already know the solution itself is 1 mole per dm cube solution of aqueous copper sulfate. But on the right hand side, the half cell basically has an inverted test tube or inverted tube where you're going to be having a platinum block as an electrode. The wire itself is made up of platinum. And there's going to be hydrogen gas bubbled through the tube on the surface of the platinum at a pressure of 101 kilopascals or 1 atmosphere. So there's going to be bubbles seen on the surface of the platinum wire and the platinum electrode. There's going to be a small hole in the tube, so if there's high pressure of hydrogen gas, it can escape. The electrolyte is also going to have hydrogen in it. In what sense? The electrolyte is going to have 1 mole per dm cube concentration of hydrogen positive ions, which means any acid works. But the condition is that you should have hydrogen ions in it at 1 mole per dm cube. This half cell is known as standard hydrogen electrode SHE. So SHE, standard hydrogen electrode, has some conditions. The pressure, the temperature, and the concentration of hydrogen ions. In the middle you have a salt bridge. A salt bridge is basically an apparatus used to complete the circuit. A salt bridge has a concentrated and saturated solution of aqueous potassium chloride or aqueous potassium nitrate. Now, in these two half cells, when the circuit is complete, there are two different equilibria established. On the left hand side, there's an equilibrium between copper 2 ions and copper metal, On the right hand side, there's an equilibrium between hydrogen ions and hydrogen. Both equations are written in their reduced formation. But which equation actually happens is a different question. Whichever equation happens will decide the standard electrode potential of the metal. Now, what's the definition of this? How do we define standard electrode potential? It is the potential difference produced when a half cell is connected with a standard hydrogen electrode, when a half cell is connected with standard hydrogen electrode. And then you talk about the conditions. So you say at 298 Kelvin, 101 kilopascal, which means 1 atmosphere, or and 1.00 mole per dm cube concentration of all the ions involved. So in order to understand how electrode potentials work, I want you to imagine two different electrochemical cells. There is an electrochemical cell on the left hand side where copper half cell is connected with SHE, and there's an electrochemical cell on the right hand side where zinc half cell is connected with SHE. On the left, you can see that the copper electrode becomes the positive terminal while the platinum becomes the negative terminal. But on the other electrochemical cell, zinc becomes the negative terminal and platinum becomes positive. This shows the direction of electrons' movement. On the left, copper half cell is gaining electrons, but on the right, the zinc half cell is losing electrons. Why is that? Because when you look at the equilibrium established between copper ions and copper, that equilibrium basically tends to move towards the right. You can see the red arrow right now, it's written correctly. The copper ions want to gain electrons. The copper ions gain electrons readily. And when they gain electrons, they produce copper. And that is why the copper half cell keeps gaining electrons so that the copper ions can be reduced. But on the right hand side, zinc ions lose electrons readily. They don't gain, they lose electrons. So the equilibrium doesn't tend towards the right, it tends towards the left. It tends towards the left so that zinc ions don't gain electrons, or you can say in other words, zinc atoms lose electrons. Copper ion gaining electron, and on the other hand, zinc ions not gaining electrons. This decides what kind of terminal is your electrode going to produce. On the electrochemical cell on the left hand side, the copper ions will reduce themselves, and ultimately hydrogen gas will have to be oxidized. So copper ions gain electrons, they reduce themselves, and as a result, hydrogen gas will have to be oxidized so that the electrons can be supplied continuously. But on the other hand, on the electrochemical cell towards the right, zinc loses electrons and zinc oxidizes itself. You can see the overall net equation also. Zinc is oxidized and hydrogen ions are reduced because zinc loses electron and copper ions gain electron. This is what decides what's happening. On the electrochemical cell towards the left, the potentiometer reading, the potential reading is 0.34 volt. But on the other electrochemical cell, which is between zinc and SHE, the potential reading is minus 0.76 volt. These readings are known as the standard reduction potential. Now I want you to understand the specific symbol used for standard reduction potential. The capital E basically means the potential difference, also known as electromotive force. It's a potential difference when compared with the SHE. So it's a potential difference between the half cell and SHE. And when we talk about that symbol, This symbol on the top is basically for standard conditions. These standard conditions basically mean 298 Kelvin, 1 atmosphere or 101 kilopascals, and then 1 mole per dm cube concentration of all the ions involved. If you have multiple ions, they all should be in 1 mole per dm cube concentration. This RED means that you are going to be talking about the potential produced when the half cell is reduced against SAG. So it's a reduction half equation. You will always see reduction half equation. For example, the X ions gaining some number of electrons and becoming X atoms. The standard reduction potential is always compared with SAG. So it's not the potential value, it's basically the potential difference. The standard reduction potential could be a positive value or more than 0 basically. Or it could be a negative value, which means obviously the value is less than 0. A positive value means that the ions tend to gain electrons readily. They want to reduce themselves. So ions gaining electron easily means that reduction is happening. And that's why a positive value. This happens when there are less reactive metals because their ions gain electron and become metals. So metals are stable. Negative potential value means that ions don't gain electrons, so reduction is not happening. Ions do not gain electrons readily, and this happens generally using more reactive metals. Positive reduction potentials are generally for copper, silver, for example, platinum, mercury. And when we talk about negative reduction potential values, we are talking about reactive metals like zinc and lithium. I hope these ideas